Okay, thank you very much. So it's a pleasure to be here. I will explain to you how at BBVA we built a classifier to distinguish or tag money transfers based on text, and also how we built it with Spark and the lessons we learned in the way. So this is especially about lessons from the data science point of view, but if you want to touch other topics, we can discuss later maybe about development details or other things. So this is joint work with Luis Peinado from BBVA Data and Analytics. We are a spin-off company from the BBVA bank. The bank created that company 3 years ago to specialize in data science. And my name is Jose Rodriguez. I'm leading one data science team. To give you an idea of what we do, this is our goal, is to improve user experience in retail banking products using machine learning. And since we are at the Spark Summit, we will see one of the tools that we built with Spark. So first of all, to give you an idea of what we mean by that, let's see 3 specific examples of tools that we've enabled with machine learning and actually Spark. The first one is this tool that we call the dashboard view of expenses and income. So I don't know how your bank displays your account transactions in your app, but we are proposing to do it this way. Not only proposing, this is working since 1 year ago in Spain. So when you want to see the expenses of the current month, you will have this dashboard view where the expenses are grouped by categories, and you can click on the categories, see the total expense in the current month, and then eventually see the individual transactions that belong to this category. So the categorization process is an algorithm that mixes several components, but one of the components is built with Spark. This is another example. We call that the anticipated expense tool. So it's basically also a section of the BBVA website or app which allows the customers to plan their month ahead. So based on the expense histories in each category, so basically we analyze the history and produce forecasts and show relevant forecasts to the user in this tool. So we produce forecasts for upcoming expenses in certain categories, such as groceries and so on. I try to identify recurrent patterns, very punctual recurrent patterns, and in some cases we also insert upcoming individual operations into a calendar. Okay? So this one, in this project, we contributed with the forecasting algorithm. It's a supervised learning algorithm that was developed in Spark, makes heavy use of MLLib. And there is not a single rule hand-coded into that system. Everything is based on data and supervised machine learning. And a third and last example is this tool called Customer Comparison Engine. So here, in this part of the BBVA app, the customer can compare their expenses in several categories with respect to expenses of a reference group. For instance, their neighbors or people with the same age or people with the same salary. So this gives this meaningful information. Customers can take own decisions or can draw own conclusions, like I'm paying too much in my internet bill compared to my neighborhood. And also the statistical analysis was done with Spark and the data frames, custom column functions, and so on. So here were 3 examples. We contributed here with the statistical algorithms behind them. And there was one common challenge to all these, to enabling all these 3 products, which is that for all these 3 products to work, we had to categorize every bank transaction in the bank of every one of the 5 million customers every day. Okay, so as you can imagine, our team spent a significant amount of work in this specific problem, categorizing bank transactions. So we are going to deep dive into that problem in the next slides. So categorizing bank transactions. We work with a data science cluster in the bank. So it's built on a Hadoop distribution and has the typical ecosystem tools like Hive, Spark, and so on. So we received 7 million daily operations from the bank to our data science cluster. And an account operation, in simplified terms, looks like I'm illustrating here. So basically, you can think of it as a row of some table, which contains fields like an operation code, for instance, 464, an amount, a date, a description, and so on. And you can also imagine that in the cluster there are other data sources that also come from the bank, where you can cross basically both. You can query for one identifier that you find in an account versus another table. For example, if the account transactions refers to a bill or a card transaction, then you can cross it with with other tables and get extra information. Okay. So now, how do we get this into a category? So of course, if you imagine the diversity of things that happen in a bank account, there is no one-size-fits-all solution. So we resort to whatever criterion we believe will categorize. And thinking like this, we started first noticing that some operation codes already reveal the category. For example, there are some operations code which refer to specific providers. Then if the operation code is not enough, you may find an identifier in one of the fields which you can cross then with a category. Or if you don't find an identifier, you can try to identify a string which has high probability to be a company name and then categorize based on the company name. Or as I will show later on, we can also inspect the description field of the transaction and apply some text analytics there. So this was the picture when we started. We were using several tools from this Hadoop ecosystem. It was also new. It was a new activity in the bank also. So we are mixing things like Hive or things like Lucene with also things like Spark and MLLib. But this was like a few components that were used to try to categorize the transactions. And of course, there are many other rules. And the goal of this is, at the end, to attach a tag to each of the transactions. In this case, the tag could be, this is gas bill. So this is one of the valid categories. There are other categories shown here for illustration, like groceries, public transport, rent, health insurance. But these are just examples because in total we have about 60 categories. OK, so one of the lessons learned when you work in data science is that simple solutions work well, but they work well for the low-hanging fruit. OK? So it means we were able to categorize many transactions with these, I would say, almost direct approaches. But then when you've done that, you hit the next difficulty. And there is a type of transactions which were very crucial for many applications and that were not so easy to categorize, which are the money transfers. Okay, money transfers is when you go to a specific section of the website and say, I want to send money to that account, and then you have to type a description of this operation. So basically, what makes this difficult is that there is no identifier, no company name that comes in a specific field. There is an operation code, but which means this is a transfer. And the only usable part of this transfer is the description that the user optionally wrote when making the transfer. So the first solution we found to that was pretty easy, which is we created a category called transfers. Okay, so then it was straightforward to categorize. But then some of us in the team were coming from a machine learning background and had touched some text analytics, and then we were identifying that some of these transfers came with text that was representative of categories. For example, in this example, if you have a text which says payment rent October flat 15, then a more appropriate category is household expenses, which is one of the other valid categories. Okay, so this is like the setup of the problem we faced, and which will take the rest of the presentation, which is how to categorize money transfers by the text the users write. And about 10% of all the operations in BBVA are transfers, so we have more or less 700,000 daily operations to classify. And by the way, it was the first time that we tried Spark, so this presentation is also about sharing the learnings during that process. Right, so from the data science point of view, for those of you who have worked in data science, you may identify yourselves with one of these challenges, but just listing everything that made this difficult. First, we had never worked with this data source. So we had to work in this mode of discovering whilst working on it. We did not have a labeled set to train a model. A fraction of transfers had text that was useless because they just write transfer or a number, so it doesn't have any content useful to classify it. The distribution of categories is very unbalanced, so lots of transfers about rent and household expenses, but not so many about other, for instance, insurance, because this is something you don't do with a transfer. We have to decide when we make a mistake whether we prefer false negatives or false positives, and we do prefer false negatives. So we prefer to. So what will happen here is we will assign the tag transfer to all the transfers, and then we will only change to a more specific category those where the classifier has a more accurate category. So we prefer false negatives. And then the text is very short. It's not even natural language. You cannot train it on. There does not exist any external corpus which has exactly this distribution of words. OK, so these are the challenges. So just jumping directly to the solution that we proposed. So this is the basic pipeline. This is classifying transfers, every transfer in VBVA in Spain since 2016. For those of you who have worked in NLP, you will recognize this is a quite standard pipeline. So it starts with the source text, a string of text that needs to be categorized. It goes through a tokenization process. The tokenization extracts individual words, removing punctuation symbols. Then each word is transformed into a fixed length vector. So this step is called word encoding or word embedding. Then we have a set of vectors that we need to combine into a single feature vector. And this step is known as pooling. Also, in Spark, we call them reduce somehow. And then this finally reduced vector, we pass it through a classifier. So actually, our first implementation of that pipeline was really the hello world of text classification, which is TF-IDF features and a linear classifier. But it was working when we managed, to get all the details right. It was working quite OK for a first try and for being a hello world. We were working with 98% precision and 21% recall. So here, one comment is we can select the point on the curve where we want to play. And since it was the first time we were doing this, we took a point with a rather very high precision. So we forced ourselves to work at 98% precision. This gives 21% recall. It means 1 out of 5 transfers that really were recognizable. This classifier will change it from the generic category transfer to a more meaningful category. And later I will discuss some evolutions. For example, that we did a second version using, here it says tests, but it's really a version that is working, that has word2vec as the word embedding step, here in the middle of the slide, and then a pooling method that is called vector of locally aggregated descriptors that I will show later, and which brought significant improvement. A couple of implementation details. This was implemented in Scala for Spark, used a lot of MLLib classes. We had to adapt some of the classes at the time we wrote this. For example, we wrapped the MLLib classifiers with a one versus some MLLib classifiers with a one versus all classification process, and we implemented ourselves the VLAD that I'm going to discuss later. And we also used, programmed this set of steps as an abstraction that then gets instantiated for each particular combination of methods with the good properties of Scala in terms of dependency injection. So I wouldn't say that building the classifier was the biggest challenge. So we found other challenges that made the whole end-to-end process quite tough. So the first one is, where do I get a data set from? So there does not exist any public resource which examples of categorized transfers, and for the categories we want and for the words we want. So we tried 2 strategies here. The first strategy is, OK, we have a lot of operations that are not transfers that we know how to categorize easily. So for these operations, we know like the X and the Y, right? So we know we have the data and we have the labels. So we could try to learn a classifier on those operations and then apply it to transfers where we have the X but not the Y, okay? And we tried that. Here the qualitative results were good, but the problem here was that, so we did some refinements. We never arrived to a point where we had high precision. So this method is good. For those of you who know the evaluation in terms of precision recall, this method is better in recall than in precision. So it's good to find candidate transfers that could be candidates to change labels, but it's not good in the opposite. Okay, just give me a few, but where you are sure that these have to change labels. So at the end of the day, we had to resort to the traditional method, which is we just take transfers, we take a portion of the transfers. So we did a stratified sampling per month of transfers of the previous year, and then we had to annotate them manually. Okay, so we annotated more than 40,000 transfers manually. So when I said manually, it was not us tagging transfer one by one. It was actually us, but we resorted to a few hacks to make the thing a bit faster. Okay, so basically we built in the short story. This would be the topic of another presentation, but the short story is we built an annotation interface where you could assign tags to categories, and then there were a few systems behind that could propose categories for the not yet annotated samples, okay, by rules or by pre-training the classifier on the already annotated ones, so that the task of annotating was easier. Now it was not assigning a label, but it was just maybe confirming tags or replacing them when they were not correct. But building this dataset was crucial to reach the performances that I'm going to show later. Okay, so we have this dataset for all the models we've trained. Now, as I said before, a second improvement was not to use TF-IDF, but to try with word-to-vec embeddings and VLAD pooling. So the good thing of word-to-vec, I guess most of you know that word-to-vec is a quite popular method to get word embeddings. The good thing of word-to-vec in Spark is that, as this example shows, with few lines of code, you can fit a word-to-vec to a big unlabeled dataset. So basically, we fit a word-to-vec to millions of unlabeled transfers, also from the previous year. So what word-to-vec does is it assigns a vector to a word, such that two words will have similar vectors. That should mean that the two words have a semantic relation. So here we see some examples of some words and the closest word in terms of Euclidean distance between those vectors. And for example, here we see the word viaje, which in Spanish means travel. So the closest words to travel are words that could be translated into tickets, flight, hotel, reservation, tickets, and so on. So what this is telling us is that this word-to-vec is really grouping words by topics, and this is a good property if you want to classify, to make a good job in classification. So the other example is rent, where you get words like flat, property, garage, and so on. And the other is payment, where you get invoice and all the possible abbreviations of invoice. And that's to get that was to get the word embeddings. Now the problem is you have n words in your transfer, and then you have to pull this single vector from all these words. So you could do that with an average, as many people do actually, and it works well. But to me, it doesn't make sense to average rent with October, because these are words which have different meaning, and then it goes. You compute the mean of that, and then the classifier will pick up some signal, probably from the word rent. But this is a more principled way to do that, and basically, is a work which worked well in computer vision a few years ago. Now it's been outdated by all the deep learning works, but this is the way it used to work in computer vision before deep learning, or related methods such as the Fisher vector, which are related to that. But anyway, so the method works as follows. First, it's doing a clustering of many word vectors word-to-vec embeddings. Okay, so it comes up with k clusters. Okay, here they are represented with circles. So then for each word in the sentence, it will assign it to the closest cluster. And in that assignment, it will compute a quantity called the residual. So the residual is the difference between the word embedding and the cluster center. And then what you do is, for all the words, you accumulate the residuals with respect to the closest clusters, and then you concatenate the residuals. So as you can see, this is quite simple to do in Spark with maps and reduce and so on. So it has been shown, and I've put in a reference here, but it has been shown empirically and also with theoretical arguments that this way to pull vectors is very effective and yields to a very good final vector that you can then send to your downstream classification process. So finally showing some results after all that. So we evaluate with precision recall curves, and as I was mentioning before, we try to be on purpose on the part of the curve which gets a very high precision. And in particular, we force ourselves to work with a precision of 98%. This is because it's a requirement. We say we only tolerate 2% of mistakes in this detection of transfers. So the result of TF-IDF, the hello world, which I said before, it was 21%. If you use word-to-vec, you improve a bit. If you use word-to-vec and add a feature, for instance, the amount of the operation, it also improves. So the amount gives some information of the category. But finally, when you combine the word-to-vec embeddings and the VLAD pooling that I just described, you get the best results. Okay? So we could now push the button and put this into production. So we are not doing that yet. Why? First, so word-to-vec is a patented algorithm, and it's not clear how to work in that space. But more importantly, in parallel, we have been developing a new multi-word embedding method, which yields similar accuracy, and we hope to publish it soon, and then we won't need the word-to-vec plus VLAD anymore. But to me, it was from the experience point of view, it's nice to see that this combination worked. I was not aware of other works using word-to-vec and VLAD to classify text. So as I did before, this has enabled these 3 examples that I showed at the beginning. But then this is an anecdote. After working on that, we had another request, a new also functionality that BBVA has, which is called Economy, needed to identify rental payments. So we reused all this work to actually do that for this app. And I'm not going into detail in the rest because the time is running. But the other, I wanted to make the observation that when you assign a tag to transfers, now you can do analytics based on the tags that were not possible before. For example, tell me how many rentals you have per day, or tell me transfers categorized as travel, which contain city names, so you could know where people are traveling to. Okay, so this is just these are real examples. We are not using them in products, but it's just to show that you could do this type of things. Also, if I had to highlight a takeaway of what was most difficult, it was not building the model or work developing the VLAD or any of these parts. In fact, that takes a short time. So the TF-IDF probably takes you a couple of days to set it up, and the VLAD with word-to-vec maybe 1 week, maybe with the implementation of VLAD a bit more. But then what took months is iterating. Okay, I have this system. It was trained on 40,000 elements. Now put it, at least in test mode, into the 700,000 daily transfers that you have. Check that everything is correct. Oh, you identify a failure, go back. And we did things like adding a blacklist, so to like sensitive words, not classify anything. We built our own system to monitor some features, as suggested by this very good reference of Google, Rules of Machine Learning, Best Practices for ML Engineering. And well, at the end of this process, we are happy with what we see, and we check. We still have some mistakes in classification, but we have visually tested that they stay within this 2% of error that we tolerated. So, arriving to the end of the presentation, I hope at this point I've convinced you that Spark helped us in this case, building a text classification system using Spark and MLLib, transferring the results to enable 3 or actually 4 real products that are running in the app of the BBVA. And from the data science point of view, so we are happy to have put such a system in production. I think it was one of the first attempts to do something with Spark in our company. And we are doing ongoing work in improving the embedding method. Thank you very much, and thanks to everyone at BBVA who also made using Spark possible, because it was not an easy job. Thanks.
Thank you very much. That was a great talk. And we are now ready for your questions. Please be so kind and come to the microphone in the middle of the room.
Hi, it was a very clear talk. Thank you very much. I was wondering if you can use external data to help you to label the transfer. For example, I guess the rent comes mainly at the beginning of the month, and the amount is a substantial part of the income, things like that.
Yes, thank you very much. This is an excellent question. And actually, I went very quick through this, but this plot over here, the one at the top, is actually the number of payments of the category rent that come by date, okay? And this period that you see is actually the start of the month, because in most cases you pay your rent at the beginning of the month. We did some tests where we tried to use that as a feature. The test was not conclusive, so we are not adding that. As I said before, one thing that worked was adding the amount of the operation. As you see in the third row here, had a small lift. And yesterday, while we were in the cocktail, someone mentioned you could have also used the network of transfers, right? Like the destination. For example, if you pay a rent to an account, it's probably an account that receives many other rental payments because it's an agency who deals with rentals. And we haven't started working on that yet because we exploited the signal that was most clear to us. But I agree, we still have many other signals to help us either doing a better job or trying to get a labeled data set that we then can confirm or reject manually.
Hi, thanks for your presentation. I have two questions. One is the VLAD. So in your practice, how many number of clusters do you use? So it's K.
Yes, the K for the VLAD. So I should query my memory for that, because it's a long time ago. You refer to the number of clusters here. I think we used 50 clusters, okay? But here the actual value is not, so there is a range of values where then the accuracies don't change that much. Okay. But I think these results were with 50 clusters. Yes.
Just to want to get your best practice. Okay, my second question is, yes, for TF-IDF, I guess you use word-based or a character-based tokenization, because you mentioned that user might misspell their message.
Yes, good questions. Yeah, I'm aware there's a lot of work in deep learning these days where, especially it's common to use n-grams or even characters one by one to pass it to a system instead of the sequence of words. I think that would make a lot of sense in this case because we saw that people do misspell things. And actually, in not belonging to that work, but in another exploration, we had to do, it was a different project, but we had to do matching, finding, let's say, transactions that are similar by text. And when we defined a distance between character n-grams, it was actually capturing these misspelled sentences. So in global, the answer is, I think it could work. For this implementation, we are not considering that because we wanted to reduce the variables of the experiment to the minimum once so that first the use case work, and then we explore all possible variations. Yep. But I think it makes a lot of sense, especially if we go for deep learning techniques.
We have time for one last question.
I have a question about the amount of data. You said that you have 700K transactions, and you labeled 45K.
Yeah.
But then for the testing, more or less, how much data you use?
So yes, thanks. That's also a good question. I see where you want to go because we've discussed that a lot of times. So for this 40K, we did a training test split. So I think in the last run we did 50% for training and 50% for test. So this is interesting because it means you can evaluate these accuracies are evaluated on the these accuracies are evaluated on the test set. And then so before working here, I was working in academic research, and you never find this situation when you write a paper that you write a test set and that you're done. So here you evaluate on the test set, and then you have to classify 700,000 every day. That how do you evaluate that? So it's part of the learnings and part of the challenge. What we did is what I said. So lots of visual checks, manual checks, automatic monitoring. For example, you can monitor how many times this transfer that contains this word is categorized as this other word. And then if you get a regular stream, like in the uppercase, it's okay. If you get a sudden change in behavior, it means you may have touched something in the last commit, or that this day was very special. Something happened that day that lots of people make transfers with a certain intent that was not captured. So this was part of refining the process.
Thank you.
Thank you so much. Let's give Jose a round of applause.